Hello, I'm the Math King, and this video is my presentation on basic derivative shortcuts. As you watch this video, if you find that it is in any way useful to you, I hope you'll give it a like and that you'll consider subscribing to my channel. Anyway, here it goes. So the limit definition of the derivative is given as this. It's the limit of that fraction. Um, so that's the derivative of f of x or f prime of x. And if you use that definition to find the derivatives, you probably would find that it's a little bit clunky and it's cumbersome really for any but the most trivial of derivatives. So my hope in this video is to really provide you a few shortcuts that will help you circumvent this definition so you don't necessarily have to use it. You could use something more efficient. As I illustrate these shortcuts, I'm going to restrict myself to taking derivatives of functions of x, and generally I'll be taking derivatives of those functions with respect to x. So anyway, here goes. So the first thing I want to talk about is the derivative of a constant. Now, numerically, the meaning of a derivative is the rate of change of something, the rate of change of a function. So if a function is a constant, then by definition, it doesn't change, or its rate of change would be zero. So because of that, here is our first shortcut. If c is a constant, then the derivative of c with respect to x, or really with respect to anything, the derivative of c would be zero. So here's our second shortcut, the derivative of x. And again, I'm generally taking derivatives with respect to x, which means I want to find out the rate of change of x with respect to itself. Now, from a geometric standpoint, we know that the derivative of a function would represent the slope of its graph. So if the function is x, the graph is the graph of the line y equals x. It's a line that has a slope of 1. Therefore, the derivative of x with respect to x would just be 1. So there's another shortcut. We don't need the definition. We could just say that. All right, so what if we have a constant times some function? Well, if f of x is a function and c is a constant, then c times f of x would be some other function of x. So we should be able to find its derivative by using the derivative definition. So we're going to go ahead and do that. So I want to find the derivative of a constant c times f of x. So using the definition, it would be the limit of what I have shown in the bracket. Notice that in the numerator, c is a common factor, so we should be able to factor c out of that fraction. And because of the way limits work, because of limit properties, we should in fact be able to factor c out of that limit. And one thing, hopefully, that we immediately recognize is that what we have in this bracket here is essentially f prime of x. So therefore, we can say that the derivative of c times f of x with respect to x is really c times f prime of x. So there is our third shortcut. Essentially, what the shortcut tells us is that the derivative of a constant times a function is equal to that constant times the derivative of the function itself. Okay, so what if I want to find the derivative of a sum or a difference of two or more functions? Well, we'll start to talk about it by taking a sum of two functions. We'll say f of x and g of x. So both of those are functions of x, which means that when we take the sum of them, we would get another function of x. So we're going to define it that way. We'll define a function h of x, which will be equal to the sum of the two functions f of x and g of x. And again, not knowing the derivative out of hand, we could obtain it by using the derivative definition. So if h of x is equal to f of x plus g of x, then h of x plus delta x is equal to this. It's equal to the sum of f of x plus delta x plus g of x plus delta x, blah, blah, blah. And that would be how h prime is formed, really just the definition. And then I will substitute what h of x and h of x plus delta x really is to give us this. The next move we can make in evaluating this limit is we can make an algebra. We can sort of regroup things a little bit in that numerator to give us this. And then we could use some more algebra. We could recognize that it would be the sums of the limits of two fractions, these fractions, f of x plus delta x minus f of x over delta x, and g of x plus delta x minus g of x over delta x. And again, we might recognize each one of these limits. This first one, that would just be f prime of x. And the second one would just be g prime of x. So in other words, the derivative of h of x, which is would be the derivative of the sum of the two functions f and g, is just f prime of x plus g prime of x. Or in other words, here's our shortcut. So essentially what this shortcut is telling us is that if we have two functions and we're adding them together, the derivative of the sum of the two functions is really just the sums of the derivatives of each of those functions itself. And we made the argument when we took the sum of the two functions. You could make a similar argument if instead you had a difference of two functions. So we could generalize. We could say that the derivative of f plus or minus g is the derivative of f plus or minus the derivative of g. And again, we've made this argument using two functions, but as it happens, you could apply this argument to an arbitrarily long combination, I should say linear combination plus or minus of a whole variety of different functions. I'll let you ponder as to why that might make sense. Okay, but let's go on to another shortcut, which has a special name. Called the power rule. And what the power rule is a derivative shortcut that will enable us to efficiently find the derivative of some power of x to the n. And this power rule applies for really any real number n, but to figure out where it comes from, to do a partial proof, if you will, we're going to restrict n to be integers. And to figure out what might be the rule in this case, we'll start off with stuff we already know. We know that the derivative of x is just 1, or we could say alternatively, we could say that the derivative of x is, say the derivative of x to the first is 1 times x to the 0. Right? So we know that already. We know the derivative of x is just 1, which if we felt like we could write it like that, you might not feel like doing that, but I have my reasons, as I hope you'll see in a minute. To find the derivative of x squared, we could use the definition of the derivative. F of x is equal to x squared. So when we apply the derivative definition, we get the limit of this fraction. And to evaluate this limit, we would probably want to start off by expanding that thing that I just circled in yellow, which would really be x plus delta x times itself. We could FOIL that out, and when we do, we get this. One thing that we see in this fraction is that, okay, we have x squared and then we have minus x squared, so those cancel, and then the remaining terms in the numerator all have powers of delta x, so delta x is a common factor. To evaluate this limit, we could factor out delta x in that numerator. And as long as delta x is not allowed to be 0, which is really not in the limit, it's approaching 0, we could cancel these guys out in the numerator and denominator. And then, so we're really evaluating the limit of 2x plus delta x, and then to evaluate that limit, you can generally at this point just substitute 0 in for delta x. So the derivative of x squared is really just 2x, or we could say 2 times x to the first. So we saw that the derivative of x, or the derivative of x to the first, is just 1 times x to the 0. And we now see that the derivative of x squared is 2 times x to the first. We'll do another derivative. Let's say we want to do this for x cubed. And again, we can apply the definition, the derivative definition, that is. So that's how it starts out. The derivative of x cubed would be the limit of this fraction. And again, to evaluate this limit, we would be forced to expand that out, which is really x plus delta x times x plus delta x times x plus delta x. You could multiply that out really 2 parens at a time, or if you're lucky enough to be familiar with the binomial theorem, you could expand that out a little bit more quickly. By whatever means you do it, this is what you'll get. So the thing that I've circled here in yellow is really all of this that I'm circling right now in yellow. Okay, and so we're evaluating the limit of this ugly fraction, but that's not so terrible. We see that in the numerator we have x cubed minus x cubed, so those cancel out. And then what remains in the numerator are all terms that have varying powers of delta x in them, or in other words, delta x is a factor in that numerator, so we could factor delta x out. And then from here, okay, we have delta x cancel out of numerator and denominator. And then once more, to evaluate this limit, we could just set delta x equal to 0. And so we find that the derivative of x cubed is 3x squared. So the derivative of x to the first is 1 times x to the 0. The derivative of x squared is 2 times x, or 2 times x to the 1. And the derivative of x cubed is 3 times x squared. So at this point, you might be able to discern a pattern. Can we generalize that pattern? Well, again, this shortcut that we're developing, it applies for any real number n, but to sort of tease out this pattern, we're going to restrict n to being an integer. So we're going to use what we know from our previous work to try to find the derivative of x to the n, again using the definition of the derivative. So we'll start off like this, and then we're left to expand that out. Now again, what I've circled in parens is x plus delta x times x plus delta x times x plus delta x, really n times, right? We're multiplying x plus delta x times itself n times. We could expand that out for whatever number n is by doing it 2 parens at a time, or once again, if we knew the binomial expansion, we could expand it out quickly that way. Any way you slice it, you get something like this, and I've tried to summarize what goes on here. Expand out the quantity x plus delta x raised to n. What you will always have, really, for n being any number greater than or equal to 0, you start out with x to the n plus n times x raised to n minus 1 delta x, and then you would have these other terms in the back that have higher powers of delta x in them, regardless of what n is in the expansion. You'll get something of this form, x to the n plus n times x to the n minus 1 delta x, plus some other terms that have higher powers of delta x in them. So when we try to evaluate this limit, we see once more we have x to the n, and then we have minus x to the n, so those cancel out. And then what's left in the numerator are all terms that have delta x as a factor. So we should be able to factor out delta x from that numerator to give us this. So we're left with, in parentheses, n times x to the n minus 1. And then what will follow, depending on how high the integer n is other terms that have some powers of delta x in them. And to evaluate this limit, we can cancel out delta x from numerator and denominator. And at this point, just like we've done in derivatives of lower powers of n, we can evaluate this limit by just substituting 0 for delta x, and we're left with n times x to the n minus 1. So there is the general pattern, and so I want to summarize the shortcuts that we found. The derivative of a constant is 0. The derivative of x with respect to itself is 1. The derivative of a constant times a function is the constant times the derivative of the function. The derivative of a sum or difference of two or more functions is the sum or difference of the derivatives of those functions. And this last thing that we found, known as the power rule. And again, we derived it essentially for n being integers greater than or equal to 0, but you'll see later on, as it happens for any real constant n, the derivative of the power x to the n is just n times x raised to n minus 1. So these are some basic shortcuts that we can use to really expedite our work in taking derivatives so that we don't necessarily have to use that definition of the derivative all the time. So let's try to do some examples of this. So here's an example. So I want to find f prime of x. First off, when f of x is 12, and then when f of x is 5x cubed. Okay, so the first one, part A, f of x is 12, so f is a constant. We know from our first shortcut the derivative of a constant would be 0, so f prime in this case would just be 0. Now for part B, we had that f of x is x cubed, so the derivative of f of x would be the derivative of 5 times x cubed with respect to x. So we could use that third shortcut. The derivative of a constant times a function is the constant times the derivative of the function. So we have 5 times the function x cubed. So according to that third shortcut, we could pull the 5 out and say that the f prime is 5 times the derivative of x cubed. And then to find this guy's derivative, we can just use the power rule. So we have a power of x. So we can say that derivative, the derivative of x cubed, that is, I'm going to just carry this 5 through, and then it would be 3 times x squared. So the derivative of 5x cubed then is just 15x squared. So we were able to find both of these derivatives without really breaking a sweat. And again, I would submit that if you were to use the definition, you would find that this process would take you a lot longer, but you'd arrive at the same thing. Okay, so let's do another example. And I want to apply the derivative in this case to write an equation of a tangent line. Now, one thing we know about the derivative and its meaning is that it's the slope of a graph of a function at a point, which would be the same as the slope of the tangent line to the graph at that point. So using that, I want to write the equation of the tangent line to the function 2x squared minus 5x plus 6, where the point of tangency is 2 comma 4, which means that, so I'm writing tangent line, so I need the slope of that tangent line. Because of the geometric meaning of the definition, the slope of the tangent line would be the derivative of the function at that point. So I can say that, I'll start by saying, well, f prime. So the derivative of this polynomial, it's the sum of 3 different functions, but it would, to find the derivative, I would just find the sum of the derivatives of each of these functions. What's the derivative of 2x squared? What's the derivative of minus 5x? What's the derivative of 6, right? The derivative of 2x squared would be equal to 2 times the derivative of x squared. The derivative of x squared, because of the power rule, just be 2x. Let's see, we have minus, well, the derivative of 5x would be 5 times the derivative of x. The derivative of x is just 1, so the derivative of 5x would be 5 times 1, just 5. And then the derivative of 6 is a constant, so its derivative is 0. So f prime then is really just 4x minus 5. Now, we use this derivative to essentially find the slope of our tangent line. The slope of the tangent at the point 2 comma 4, really because of what the derivative means, the slope of the tangent would just be f prime evaluated at that point, or f prime of 2 So that's 4x minus 5, so that would be 4 times 2 minus 5, or 3. In other words, 3 is the slope of the tangent line that we're looking for. We want that tangent line to go through the point 2 comma 4. So at this point, we could use point slope to get there. I could say y minus 4 is equal to the slope, which is 3, times the quantity x minus 2. And if I wanted to rewrite it so that it looks like, mx plus b form, I could say that, okay, well, y would be equal to, and I'll distribute here, we'll say 3x minus 6, and then I'm going to add that 4 to both sides. So plus 4. So that would give me y is equal to 3x minus 2. So there is that tangent line to the graph. Okay, and what I want to show you is a graph that I made using Desmos, really a graph of both the function and its tangent line. So the red graph is the graph of the function 2x squared minus 5x plus 6, and the tangent line that we found just now was 3x minus 2. And we can see it certainly looks like it is the tangent to the graph at that point. So there we go. So there's a summation of some 5 basic shortcuts to derivatives, which hopefully will make your derivative taking life a lot easier. There are many more derivative shortcuts, but I wanted to start off by giving you these basics. So again, if you find this video useful, I hope that you'll like it, and I hope that you'll consider subscribing to my channel if you haven't already done so. So this is the Math King signing off.